Good afternoon, everybody. My name is Mauricio Orantes, and I'm from the National Universities of Mexico. This project was supported by the National University in Mexico and by the School of Engineering of the University of Newcastle in United Kingdom. This project is called Intensified Microalgal Biomass Production in a HRAP using nutrient-rich wastewater. As a content, we have the background, the main objective, the materials and methodology, the results, and many conclusions and questions you have. But as a background, microalgae-based wastewater treatment were proposed in the early in the 50s. Microalgae has the capability or possess the feature remediation capability. They have this ability to eliminate contaminants in liquid or gaseous phases. This is for two purposes. The first one is the wastewater treatment, and the second one, we can produce a biomass. This biomass, we use it as a commercial purpose. There are many advantages, and there are many disadvantages. As advantage, we have low energy requirement. Microalgae can be used as raw material for biofuel production, and they can remove nitrogen and phosphate to produce biomass. As a disadvantage, we have low biomass productivity in wastewater, high cost of biomass separation, and required a big area. Well, this is the main problem of our project: low biomass productivity in wastewater. So, in the microalgae cultures, there are many limitations. We have three: physical factors, chemical factors, and biological factors. In this project, we are really focused in chemical factors about nutrient availability. You know that in wastewater we have nitrogen, nitrogen, and phosphate, and other many macronutrients that microalgae needs to grow out. Well, this is a really big limitation to produce biomass. Our project consists in the next way. We use the wastewater as a nutrient source. In this project, we have a supplementation with alternative nutrient flux. In this case, we are using cold manure digestate, organic fractional municipal solid waste digestate, and human urine. This is for intensified the microalgae production. After that, we have a microalgae cultivation. A main activity in this part is the treat with water. And the second part, we recover the biomass for produce many products like biofertilizants, biostimulants, biofungicides, biodiesel, bioethanol, bioplastic, by other ones. In this figure, in the figure number 1, you can see our batch culture of microalgae in high algal ponds. This is a phototrophic process. We have many of these ones with different capabilities, per liters to 1 meter cubic. Well, the main objective of this project was to improve microalgal biomass production by treating wastewater supplement with nutrient-rich liquid weeds and high-rate algal pond, RAT, maximizing run and nutrient mobile. Well, our workplace was that. And this figure, in the letter A, you can see our pilot plan for the evaluation of wastewater and microalgae accidentally at UNAM and the National University in Mexico. In the letter B, you can see the water canals and Chinampa in Xochimilco, Mexico City. Xochimilco is a World Heritage for our country. It's really important for our country because this is the main place for ajolote. Ajolote is one of our national species in Mexico. And this is our team group, and this is our laboratory in the university in Mexico. Sí, gracias. And now we have many materials. We use these liquids as alternative nutrient flows. We use this cold manure digestate, human urine, and organic fraction of municipal solid waste. The necessity to use the cold manure digestate and human urine was because in Mexico, we are working with a sorry, I forget the word, but it's it's a chinampa. In this chinampa, it's a different way to cultivate many products, vegetables and hortalizers and this kind of products. And in this place, they have an aerobic reactor, and they produce biogas, and the other product is the digestate. They use cold manure for produce the digestate. At the same time, they have dry bathrooms, and they have the human produce. For that reason, we use these two liquids. And the last one, we use the organic fraction of municipal solid waste, because in United Kingdom, it's really, really common to use this organic fraction to produce biogas, okay? At the same time, we use the water from the Xochimilco canals. We use a Desmos and Desmos microalgae bacteria consortium, and a RAC for 30 liters. Of methodology was, the first part was the characterization on the complementary liquid strengths, the three ones, the cold manure digestate, the second one, the organic fractional municipal solid waste digestate, and human urine. And the second part was microalgal cultivation in the presence of the complementary strengths. And the last part was biomass quantification and yield right cultivation conditions. As a result, we have a complete characterization of these liquids. But well, I don't have a lot of time to explain each one. But the most important for us was the rec-fill relationship. Because this relationship express how many of these nutrients we need to improve the culture in the microalgae biomass. For that reason, we can see that all the micronutrients and the micronutrients, they are not present in the liquids. We have to looking for other liquids to increase this one. Well, the culture was batch cultivation of microalgae in these high rate reactors. Was in 30 liters. We start with a low ammoniacal concentration with almost the same concentration with the same liquids. We mix this liquid with which water? Well, as a result, you can see these three figures. And the first one, you can see that the winner of this like a competition is the FMCW digestate, because we can produce more than 1 gram per liter of biomass. That is a lot for biomass production, because in other words, in other jobs, you can see the maximum production is medium gram, and we produce more than 1 gram with this mix of which water and these liquids. In the other figures, you can see the nutrient removal. Well, microalgae love ammoniacal nitrogen and nitrates, and they remove it. And in the last picture, you can see the orthophosphate remotion and what's great. Well, as a second part of our project, we use ozone with a pretreatment for improve the color of our products, because they have a high colors. And this is a big problem in microalgae cultures, because the turbidity increase and the light is not allowing to pass in the culture. For that reason, we use a pretreatment with ozone. You can see in this picture, sorry. I don't know what it's like, but well, you can see in the picture on the top that is a dark color, but after the pretreatment with ozone, we can see a colorless. This is the second part. We are working in this part in the institute, because ozone has a capability to oxidate every organic material, because it's a great oxidant. Well, with that, we obtain this graphic, and you can see with ozone, we have a better microalgae ground. In the line green, you can see that with the treatment with ozone, we improve the microalgae ground. And the last part of our project, we know that the carbon is a problem for microalgae cultures. and they need a lot of carbon for growth. But well, in this project, we cultivated the microalgae as a phototrophic process. They obtain the carbon source from the atmosphere. But well, we include part of this project to using sodium bicarbonate as another carbon source. But well, with that, we obtain with the next figure that you can see if we add sodium bicarbonate, we'd improve a little bit, not a lot, but a little bit, the microalgae ground. In this table, you can see our it's a comparison of previous work for my project in the University in Mexico. Somebody knows where is the light? ¿Dónde está la luz? Ahora le pico, thank you. Oh, no, creo que la he liado. Yeah, thank you. Yeah. Well, we can see the production of the biomass. In other jobs or in other projects, only produce half gram. Well, what can produce more than 1 gram per liter? Well, about the biochemical composition of the microalgae, because this is really important for us, because this is the second part of our project, because with this biomass production, we can produce biofuels. This is really important because we need the quantities of carbohydrate, lipids, and proteins. But well, with the domestic wastewater and a mix with organic fraction of municipal solid which digestate, we obtain more than 1 gram per liter of biomass. As a conclusion, we have these four. Microalgal biomass production was intensified by using mixtures of wastewater and nutrient-rich supplementary streams. Also, we have a significant removal on nitrogen, 90 and 99%, and for nitrates, 50 to 90%, and orthophosphated 42 to 82. The highest concentration of microalgal biomass obtained in batch culture was with a mixture of wastewater and FCW, organic fraction of municipal solid waste digestate, more than 1 gram, 1.2 gram per liter, and with the human urine. And the less gram was observed with cold manure digestate compared to the other ones, because this may be attributed to the higher turbidity and coloration that the cold manure digestate impart to the culture medium. Improving was achieved when oxone was used in a pretreatment. It's a reduced color and high turbidity by breaking down molecular components. And the last one, adjustment in the organic carbon containing the carbon, nitrogen, and phosphorus ratio, showing a slight enhancement on microalgae grown in the complementary strain. This suggests that inorganic carbon and other essential elements and control factors in this work should be investigated in the future studies. So many references. Welcome to Mexico and this university. Thank you, grazie, and gracias. Thank you.